All right, so we're still talking about mechanical energy and converting between potential energy and kinetic energy through the conservation of mechanical energy. So I just want to hammer this home. Um, so when we convert into potential energy or potential energy into kinetic energy, the total mechanical energy of the system is conserved. Now, this is not taking into account any additional forms of energy like chemical energy or thermal energy, but the mechanical energy is going to be conserved. In a closed system with no friction, this is a perfect ideal situation. So what this means is that when kinetic energy goes up, if the total has to stay the same, then that means potential energy has to go down. And we can see that on this diagram here, where we have at the top of our hill, our roller coaster rider has 100% of all of their energy is potential energy. They have zero kinetic energy. But as soon as they start moving down that hill, they're going to take that potential energy and decrease it while increasing that kinetic energy. So as their height goes down, their speed goes up. Is what's going on here. They're decreasing the height, they're increasing their speed. So that when they're at the bottom of this hill, all of their energy is in the form of kinetic energy, and they have zero potential energy. Now, but Ms. Due, roller coasters work because you don't stop at the bottom of the hill. Well, yeah, I know, because the momentum, right? Y'all remember that? That's that forward motion that you have when you are moving, when you have a velocity. That momentum that they have all that velocity. It allows them to continue forward, and that track pushes them up. So that allows them to regain some of their potential energy. But that means as they get closer to the top of that hill, their speed goes down. So the higher they get, the slower they go. Now, ideally, everything gets converted between kinetic and potential, and there's no loss of energy anywhere. All right, all of the gravitational potential energy goes into the object's speed as it falls, but we don't live in a perfect world. We have things like air resistance and friction that exist, and we have to account for that, or at least understand that in reality, when we take these measurements, we're not necessarily going to see 100% of the input energy transferred into our output. So potential energy, as it's converted into kinetic energy because of friction, we're going to have some of that potential turned into thermal energy. It's going to be released as heat into the environment, which is not a usable form of energy. It's not going to go into the outcome we want to see. So we need to understand that. We're not going to get into calculating that. That is for a physics class, not for this general overview of energy and mechanical energy. But I want you to understand that friction exists, and it is going to impact what your results are going to be. But for the most part, when we do calculations, especially these calculations that we're going to work some practice problems with, you're going to assume that there is no friction. So that 100% of your potential energy is going to become kinetic energy. All right, so your total energy at the beginning has to equal your total energy at the end. And that's going to be useful to give us a good understanding of what we should expect, or at least the ballpark that we should expect to get out of a device that converts different types of energy to other types of energy. But we also need to understand that that's like the maximum. And chances are we're not going to hit that maximum. It's going to be somewhat less. So how much less could it be? All right, we're going to get to that in a second. So, right, this is just a recap. Here's a cool roller coaster where you go up. This is the lift hill right here. You're going to go up here, and then once you fall off of this side, you're going to be able to go through all of these loops because of the momentum, the forward momentum that the car has from the kinetic energy that it gains as it's falling down this giant hill. That's actually kind of a terrifying drop, and I don't know if I would ride that, but I love roller coasters, so maybe. But not all of this potential gets into that speed because we have friction. So some of that friction takes some of the energy that we potentially have and turns it into heat. All right. So, and then we have how is energy being converted when you burn a match. So we strike a match and then it burns. What energy is being converted there? All right. So just think about what different forms or different energy sources do we have? Well, we've got chemical energy, right? So the wood is a substance, and that wood and the tip of the match has chemicals in it, and as those chemicals break their bonds and reform into something else, it's releasing energy. And that energy is going into electrons moving around, which is generating this radiant light energy. All right. Now, I've said that our kinetic energy is never going to fully be able to our potential energy will never fully be 100% converted into useful kinetic energy, because some of it will be lost. That's lost in air quotes, okay? Some of it will be converted to a less useful form of energy that's typically called thermal energy or heat. The way we can measure how well a device or a conversion system works to take our input energy, our potential energy, and turn it into a kinetic energy, or vice versa, kinetic energy into potential energy. The way we can evaluate these devices is by looking at their efficiency. All right, so when we talk about energy efficiency, what we're looking at is how much useful energy can we get out of that system. So here I've got, say, my potential energy that comes in to my system. My system does stuff. So this is like the car sitting up at the lift hill, the top of the lift hill. Then the car starts falling down the lift hill, and it's producing energy of motion, kinetic energy. But there's friction between the roller coaster car and the track. That's going to cause some of that energy to be dissipated, to go from that potential of that gravitational separation, that height, to the speed that it goes in. So not all of that potential energy is going to become the speed of the car. Some of it will get siphoned off, will get kind of separated and turned into heat energy that gets dissipated into the environment. In an ideal world where we have no friction, then all of the energy that we put into our system comes out of our system, all right? And comes out of our system in a useful way. And that's the big key. It's not that the energy is getting destroyed or becoming lost. It's that we're not able to capture it in a useful way, all right? So when we have these energy conversions, all of them are going to have loss of usable energy, all right? Typically, that loss of usable energy goes to thermal energy, all right? But not always, all right? And we can also capture thermal energy to use it to warm things up, right? But when we talk about things that are not efficient or energy efficiency, we're talking about some of the input energy that we put into this device is being converted into an unusable form of energy that is typically thermal energy. Now, we lose, again, air quotes around loss. We have energy that gets converted into unusable energy everywhere, all the time, from our beginning to end of our energy story here. So if we think about where we get our energy from, which is essentially all of our energy comes from the sun at one point. But it goes through all of these different changes to get to, say, the electricity that we use to light our house or our school building or to power our phone or computer. Now, we're losing, again, air quotes, we're having energy converted into unusable forms at every single step, every single conversion. So when we look at, say, the efficiency of a power plant, all right, we're burning something to generate electricity, or we're using solar panels, or we're using wind turbines. If we look at the efficiency of these power plants, most of them are about 35% efficient. So we are putting in, say, natural gas into this process that's taking the natural gas and turning it into electrical energy. And of all of the energy that comes from the natural gas, only 35% of it is becoming usable electricity. All right, so what does that tell you about how much thermal energy is being produced when this happens? If only 35% of it is becoming electricity or electrical energy, then that means like 65% of it is being converted into thermal energy that is just going out into the environment. Okay, that's kind of crazy. Now, we're talking about efficiency, but I do want you to know that unless you're told otherwise, and unless the point of the calculation is to figure out how efficient something is, if you're just looking at comparing potential to kinetic energy, you can assume that we have 100% efficiency, unless you're told otherwise, which means that when we do these calculations, you can operate under the assumption, unless you see a statement about efficiency, that the potential energy is going to equal the kinetic energy. All right? So, let me see. talk about kinetic and potential energy, we are looking at energy being converted from one to another. It's not lost or gained, it's just being transferred. So we have this cool little animation here where we can see our roller coaster going along the track. Notice our column here for total energy is not changing. All right. But based on where the little car is on the track, the amount of potential energy and the amount of kinetic energy are going to vary, are fluctuating. All right. So when we're up here, we've got a whole bunch of potential energy. But when we're down here, it's all kinetic. And then as we go through the loop, it goes up to potential and then down and some more, but it doesn't go all the way up, right? When we're up here at the top of this loop, we're at 80% potential energy, 20% kinetic energy, all right? So it's fluctuating a whole lot. All right, so when we look at this, where is the kinetic energy maximized? Well, that's here at the lowest part of our track, and our potential energy is going to be maximized up at the highest part of our track. All right, and I hate when they make things that A, you can't read, and then B, you have to click through everything. But that's just me. All right, so lots of things look at combinations of kinetic and potential energy with this conservation of mechanical energy. So if we think about, say, a pole vault, we have the deformation, like this is acting like an elastic band or a catapult. The pole bending is acting like a catapult to fling the athlete over the bar here. So we have the elastic potential energy of the pole as it bends, then being used to convert the athlete from, or then to be converted to the speed of the athlete. So we're bending the pole. That is an elastic potential energy. And then as the pole straightens, it releases that potential energy and turns that into kinetic energy of the athlete flying over the high bar up here. So we've got kinetic energy increasing as the pole snaps up. That gives the athlete the momentum to go over the bar, but the athlete now has a gravitational potential energy up at the top, so that once they're over the bar and they're not using the pole anymore, they're going to just fall. Their momentum will carry them forward a little bit, but they'll fall, and that converts to kinetic energy, and then they hit the mat, and they now are at a zero state. All right, so in the next video, we're going to do one more video. We're going to look at some of these examples and maybe go through a calculation or two of comparing kinetic and potential energy. All right, next time.